Okay, let's just get it started. Hope you guys are okay with me recording. That's okay.
Yeah, no problem.
All right, cool. So let's just kind of do this together. So first thing we want to do is actually get the data set, right? And
Right.
um, let's, we're gonna import the data sets. Let's do that. And that's okay, right? That's not good.
Okay. It says done.
Uh,
Given NumPy everything.
I can look on my side if it's there or not. I I bet it is.
To me, it looks like that's just like a bug on Torch Vision's part.
Oh no, I'm pretty sure I overrode something. That's fine. That's fine.
Alright.
Next thing we want to do is, I guess, do we want to write the network right now? Let's go back to the thing.
Yeah, sometimes I really didn't understand how they like gave these parameters, like the transforms that. Okay, normalize I do understand, but like how they set up the parameters for like the convolutional layers, like the hyperparameters. I think I have to understand how that works.
No, that's fine. Really, okay, so we kind of know what we want right now then, right? So we
Mm-hmm.
can actually, let's try that one more time. No transformations, and that's fine. We actually want to split though, right? So,
Correct. Yeah.
so we want to get train set and test set.
That's it.
Let's just look if there's an easy way to split it.
Well, they
Yeah,
just
there's
said
something in the
train
train
to
flag is equal to true and one is train is
yeah,
equal to false. Yeah.
Oh,
that's although that's kind of different than what we'll have to do for our thing.
Do
yeah,
you
it's a little. It's
normally
kind of
just
cheating, but it's fine.
do you like pick random, like 4/5 random of the data and keep it as training and then take like 1/5 for test?
I think that's how
Or
they do it in the actual.
Yeah,
okay,
that's what we do in the actual model right now.
okay.
Okay, but to this point, now we got train set test set. Now we need test loader and train loader, right?
Yeah.
What is it? So it's torch. Let me just copy all the. It really shows that I'm a noob right now. But that's okay.
I think test loader.
Computer science.
S loader.
Wait, what is test loader again? What does this do? How is this different from I forgot. How is this different from the training set?
When you actually like make an iterative thing to loop over, so say like, so you see like the batch size is 4. Every time you're gonna
Correct.
train the network, it's gonna use 4 images instead of like going
Okay,
one by
okay,
one.
train.
I think it actually
Okay,
helps
okay, okay.
with the process. So that's MNIST train set. Test set, and this looks fine to me. We'll see if it's fine with the computer. Okay, and then I guess the next thing we want to do is actually just load a couple of images. Also
Oh,
get the
you want to
classes.
create some classes? Yeah.
Yeah. What is it? It's like np.arange.
Yeah.
Yeah, you can do that.
I usually just do np.array and then int, or np.array and then just range. Although I don't know if that's slower by chance. I don't think it
Import
matters.
numpy.
SMP.
Okay.
Yeah. Okay.
That's another thing. I think we want to reshape it though, right? So we want -1 like that. That doesn't look right.
Why do we need it to be reshaped?
If we're doing
Yeah.
a classification, right, then it's one
You want
array
it to
of
be
10
like a
elements.
vector?
Sorry.
Sorry, do you need it to be like a vector, or what are you reshaping for?
I think when you do, actually, I might be wrong.
Because they just use like a normal array, right?
Yeah,
Yeah,
I
I
think
think-
so. Let me put that up there. Okay, I'll just kind of go with how the thing is telling me to do it. Next thing I kind of want to do is, I guess, plot it out to see if it works.
Mhm.
Image.
Oh wait, they didn't even use an array. They just used a tuple
What do you mean?
Does
for the
that?
classes.
Oh, do we have to? I mean,
I'm not actually sure.
we'll see. If we get, I think the whole point was just to see if we get issues.
'Cause I think in the end, the main thing that these classes are used is when you're trying to predict your
Yeah, 'cause,
losses and everything. You're just using that to like. I don't think that really.
Yeah, I think it's because it's just outputting a number anyway.
Correct.
Alright, let's see what happens.
What's this?
What is the actual issue? Data editor,
It's
train loader.
Batch less
Tensors,
contain.
PIL.
Oh, you gotta
image.
convert the images to NumPy arrays.
Oh, what? They don't do that for us?
I think it's. Oh wait, it says image.numpy,
no, it
right?
does. It does
No,
do
so
that.
they found the class PIL. So it's like a payload
Yeah,
class.
but in the code you wrote np dot or you wrote image.numpy, right?
Yeah.
Yeah. Um. It says
Let's.
images.
I guess, okay, first thing we can do is just print the image, right? Just see what it looks like. Can
Yeah, that's not gonna be healthy.
let's see something for now. Let's just print out.
Try just printing image dot numpy for image and images, or you can just do print images dot numpy.
No, so I think the first thing is we gotta see what data editor is like. Also, if this seems kind of boring, this is kind of exactly how I learn.
I think if we're gonna do something, when we start doing this, I think it's important.
Yeah, you can't print an iterator straight out. You gotta turn it to list.
Yeah.
I just want to see. Oh, I can't do that.
Yeah, you can do next data editor though.
Mm-hmm.
Like next parenthesis. Now, like next is a global function, not a member function. So like print next parenthesis data editor.
Okay.
Oh.
It's kind of whack. I don't know why Python does it like that. Oh shoot. Found class pl.image.
I think
Oh,
okay,
because
so
it's
I think
still, it's still
the
trying
one thing we
to.
gotta do is just figure out what the actual train loader images are. So if it's true that iter for in iter train loader, does that work? No. So that's the main
You
thing,
know,
right? It's still
so
images.
yeah, so I think this is actually an error that's coming from the first cell because basically train loader is like lazy. it's not actually running
Oh,
until
we
you
can
try to
change the
iterate it.
transform then, right? We can change. We can add a transform to like 2 tensor or something.
Probably.
You know what I'm saying? So like.
Wait, so what is the issue with the second cell? The
So like
second
train loader, like it's not actually running anything until you try to iterate over it.
It's just throwing
Okay.
stuff into a variable.
Yeah.
Oh god.
Oh yeah. So you definitely got to do the transforms equals transforms dot two tensor and normalize. Is that the top of the
Yeah, it's the first, I
tutorial?
It's the
think. Yeah,
first.
top of the tutorial.
Yeah.
Is it? Transform to.
The-
Oh, it
the-
is 2 tensor. Yeah, we can use that code.
Yeah.
That's the sign of computer science.
Transforms not defined. You have
you
an
gotta
S somewhere.
you gotta import transforms. Torch vision dot transforms.
Oh.
Alright, let's see if that. Okay. I don't really need this, hopefully. Alright, let's see if this works. Okay, computer.
All right. Yeah.
Wait,
I
isn't
think
it supposed to
you're
print it?
printing like the whole. Okay. Yeah.
Oh,
What's
did I
it
do
say? Now it says.
output. That's 3
where do
channels,
you
right?
use it?
That's really the issue. Let me try again. Yeah, okay, so it says the channels.
Output didn't match.
So
Oh,
where's
you have to change
what
it to, I
line is-
think, 3 channels.
Yeah. So right now it's like black and white.
Yeah, we have to
Well,
change it to
you want to
RGB.
keep it black and white, so it's the 32828, which is wrong.
Oh, for this, yeah, for our, I'm thinking of the.
Yeah.
Yeah, so where in the code do we call for 3 channels though?
Probably in MShow. So
Sure.
I believe that MShow wants 3 channels. So in this case, you do want to just temporarily change it to 3 channels.
Alright, so what would we change though?
Yeah, that's kind of rough.
AC.
Because we can't just set all of the other channels. Is there like MShow black and white or something?
Let's figure out.
Oh yeah, apparently you can do CMap equals grace.
Tensor image.
Oh, that's kind of interesting. That's basically just changing the alpha. But MShow has a parameter called CMap. And you can just set it to grays.
Okay, but is that for Matplotlib or NumPy or?
And it's matplotlib. So basically you just do plt.mshow, right?
Sure.
And in that mshow, you say grays or CMap equals grays.
Do we need this actually? One question. What do I call him show here? Yeah, okay.
That's on
Yeah. Okay, so
yeah.
what are we looking for then?
So after np.transpose whatever,
Sure.
in the parentheses, you say CMap equals grays. I
Okay.
think it has to have an E. I don't know if it matters. Oh shoot. Oh, it doesn't care. I
Let's
guess
just
try
start
this
with one
other
thing.
thing.
What if I just look at just the label to see if
Oh shoot.
Okay, so it
What?
really has to do with how it's being loaded out of the thing, right? Output with shape
Which
12828. Let's just look at what the actual thing is like. All right. What's the play then?
I think it probably is again coming from data iter.next because it's probably still in the second cell.
Let's just okay. So what's wrong with the?
Oh, you know what? I think transforms.normalize is probably three-dimensional how it is now.
Yeah.
I'm just looking up the documentation for it.
We could remove this. I just picked it out because it was the first thing I saw.
Yeah,
On this
I'm not
demo.
sure if we need to normalize this one actually.
Okay, let's just take that out. Let's just try running the code from the start. Did that work? Okay, we got
Yeah.
the labels. Let's see if this second part works.
All right, sweet. Wait,
That's
but that's
not-
So
not
wait.
exactly
That's-
imshow.
So why did you have to remove the normalize? Because I thought like it normalizes just so that you can those basically those pixels they're represented in -1 to 1 or 0 to 1 sort
Grays
of
is not
range.
available.
So why?
Yeah. So I'm not sure actually how PIL works. It looks like
I
they're
wow.
recognize, to be
already
honest.
just from 0 to 1 though.
Let's do this again.
Okay.
Okay, that's what we're dealing with.
Yeah. So like 0 to 1 is not that bad. -1 to
Okay.
1 is
Do you know
better.
when you would use -1 to 1?
Like -1 to 1 is ideal.
Okay.
0 to
Okay.
1 is not terrible.
Okay.
Actually, we should still try to normalize it though.
Do we? Okay.
Yeah, so I
Check up normalize.
believe
What do you do to normalize the image though?
I'm looking at the documentation.
We could just carry on.
So
Like
when
this
you
then.
printed the data points, was it all from 0 to 1?
Yeah.
Not the data points. I mean like the okay.
Okay, let's. Do we want to just carry on?
No, I think we should still normalize it though.
Okay. What do we add then?
Let me check.
Oh, this is MNIST, right?
Yeah. Normalizing. Normalizing.
All right. Yeah. So, remember how before the tuple had like 3 things in it, right?
Yeah, I can.
You
I
just
can
want to
actually
make
just
it
undo it
tuples
to
with
get
1.
it.
Yeah, just make it. Yeah, just remove the last 2.5.5 from each tuple.
Yeah. So what does each one do then? What is each call doing?
Maybe
It's
was that the one that was creating 3 channels?
Yeah, I believe so. You want to keep the comma in actually, because Python needs a comma to call it a tuple.
Oh, really?
Yeah, it's just kind of strange.
The programming languages. MUN lang, boy.
There you go.
Yeah.
Okay, solid.
Yeah, that looks better.
Let's just start with just the network then, and let's just work backwards to find the errors. I'm just gonna paste in
Sure.
the stuff from the tutorial. We're going with it.
And then
That's
we
fine.
can go through it line by line and explain it, I guess.
Sure.
Mm-hmm.
Okay. Unpoise I'm not gonna do because I don't even know what's going on there. Super, I can try and say it. It's just there's a bigger actual feed forward network that's being written with PyTorch. I didn't call on it because I just like to use the work that they do and then draw in some of my own things. The first thing we should start with then is the actual convolutional layers. I think the way that the documentation works, I'll pull it up on the side.
Actually, we do gotta change this.
Yeah, no, I do,
The
because the
parameters,
channels
right?
are all messed up, right?
Yeah. Okay.
Yeah.
Okay, so let me bring over conv2d for now. Just to look at that, right? We kind of know that there's something up where channels we're taking in, channels we're bringing out, and the actual kernel size. That's like the three things that we're dealing with for now, right? And so when we look at this, we're taking 3 channels in, we're spitting out 3 channels, and our kernel is a size of 5. So in this like size, in each of these images, the way that we're convoluting over is that we have this kernel that's 5 pixels by 5 pixels, and then we scan over it, we move one, we scan over another 5 by 5 area, and just do that over and over and over across the image. This will probably have to change though, right? So first thing we have to do is change the kernel size.
I think it's a 1 channel. So the
Yeah.
sorry, go ahead.
No, I mean that's right. It is 1 channel instead of 3.
Oh yeah? Okay. So that's another thing. Does it matter? Does out channel really matter here?
And
To 6?
So
that's
yeah, out channel is arbitrary. There's like some fancy math you can do to find out what's best. But for us, we'll just like kind of fiddle with it until it works.
Sure.
okay. Do you
and the
guys
next
understand? I didn't understand what the channel actually means. Like, okay, I understand maybe black and white is 1 channel, RGB is 3 channels, but let's say you want to output it in 6 channels for now. What does that actually mean? Maybe
So
on like a
that's,
graphical.
yeah, that's essentially the number of dimensions that the matrix has. So these matrices,
Okay.
they are called like hyperdimensional. Sounds pretty cool. They got like a whole lot of dimensions on them.
Okay.
So here we're taking this one-dimensional matrix and we're turning it into 6 dimensions, and we're doing math on it. And the thing about matrix multiplication is that you can basically make dimensions out of like not having dimensions, you know? And that adds like memory to the model essentially. So if we increase this to like 40 dimensions, right? The model is
Right.
gonna have a whole lot of memory, like 40 times 40, right? I don't think I did that right. But anyway, it will have like exponentially increasing memory.
Memory.
And that will make it smarter, but also more prone to overfitting. And it'll also make it
Okay.
take a lot longer to train.
Right. Right. Okay.
So 6 is probably reasonable.
image
Okay.
dimensions would
And the last one is kernel size. Is there any specific? What's this? Oh, these are 28 by 28. Okay.
Yeah.
I think I might go with 4 because 5 is not.
Yeah, that
it's not
sounds
even,
Yeah,
reasonable.
just E.
even
Yeah.
spread. Next thing I guess would come to pooling. Pooling is like once you actually get the convoluted image, I think you're trying to extract features. So I think when you pool, I can pull up the documentation as well. Just to. Also grab that. So you can kind of see like as it like goes over. I believe I might be saying this wrong, but it's picking out the largest image from this kernel, each one that it passes over, right?
Sure.
And that's I think that's how you sort of start to extract features. Because once you can do some math to kind of get like the smaller kernel or whatever, right? But as you start to pick out the image, say, let's go back with this one. I believe that like you'll pick out the largest number, and that's kind of like, oh, say you had like a corner or something, and like I guess the brightness value or something like that would be higher in this area. So like by pulling over it, we can sort of pick out what that highest value might be, and sort of start to train as to, I think, what the features are to look out for.
Okay, so it takes those sections of the convolutional layer and sort of get some number. I don't know how or what the numbers, but you're saying takes the greatest number out of. Oh
I
wow,
believe
that's
so, right? I think
Yeah,
that's how it works.
that's literally what it does, and it's kind of hard to explain like how that helps.
I mean, it helps
Mhm.
intuitively from a
think
sense that, okay, if you imagine that there's some feature that will generally be a higher number,
yeah,
if you could convolute over. So the convolution part, I think that's actually kind of the more difficult thing. Because you're just like averaging over the numbers, right? When you convolute over
um,
like a certain kernel.
it's not you're not really averaging them.
That's the thing. So the
You're
math
like
of this one is kind of something that actually still confuses me. But this one's pretty
yeah,
like straightforward in the sense that
I
we're
mean
picking
it's
out.
pretty abstract.
All right, that one's a little bit more obvious. This one I kind of actually don't know.
Yeah,
Um,
so it's like it's not something that will ever be intuitive. Um, but if you read up like a Wikipedia article about how convolutional neural networks work, it might start to make sense.
yeah, no.
Okay.
So the math
I
that's
mean,
actually
basically,
happening though, like, because we're picking out like a 4x4 each time we go over, right? The same way that this is picking out a 3x3. I think the actual thing that we were trying to figure out is what's the number here? What's the math to actually get this number? It's not gonna matter once we actually train the network, but I think it helps with the lore.
yeah, I
Right.
mean,
Yeah.
in terms of like our use case, basically what you need to know is that this pattern where you do the convolutions and then the
Mhm.
max pooling is really good for detecting image features.
Okay.
All right. Same thing will kind of happen with this next one. Do we need this many damn layers?
Yeah, I mean,
Screw
uh,
it. It's like just the first time, right? So we'll just if it
bro,
works and then
honestly,
we'll work
I feel like
backwards.
you never need more than like 3 layers, but
Screw it though.
you know,
Next thing we should go over is the linear layers, right? That one kind of
yeah,
Yeah, I
confuses
didn't
me, but this is
understand
where the
what they're
actual
for.
magic happens as far as like the I guess retrieval of features. And I guess let's just go over that.
or like figuring out what to do with the features.
Yeah. So this one has to do with the actual image size, right? What's the math to get that?
Well, the math is right there, right? 16 times 5 times 5.
Um, yes, yes,
Um,
yes.
so I believe instead of 5 times
It should be
5, you
4.
you gotta make 4 by 4, yeah.
So
And
wait,
then
what is that exactly? What does this do?
so the convolutional neural network, right?
Hmm.
Its output is like a huge matrix, right?
Sure.
16
And
dimensions.
that matrix, it's gonna be, um, it's not a cube, I don't think. But oh yeah, it's not a cube. It is a 6-dimensional matrix, and it's gonna end up having um the what's it called? Like the length of it, it's gonna be 16 times 4 times 4. I don't really remember how the matrix transformations work.
I thought it's just you
Hmm.
flatten the matrix, right? What you said.
Well, you're not flattening it, you're turning it into a square, I believe. Or
Oh, okay.
or like
What's the
a
120 do?
hyperdimensional cube. Um
What does the 120 have to do with it, though? Guess
the
that's the.
120 is arbitrary.
Alright, screw it.
Basically, what matters is that it gets down to 10 at the end.
Yeah, because
And
that's the
10
10
is,
digits we're gonna predict, right?
yeah,
Hmm.
so we could just remove that FC2 layer. Um, or we could just make FC1 go straight from 16 times 4 times 4 to 10. It would not be great, but um, it would be possible. It wouldn't error.
Would
Um,
that 120 be the number of neurons in that layer?
yeah, yeah. Well, 120 times something, I believe.
I can put the documentation right here just to see it. I don't
I mean,
know what it actually means.
I
It's just
don't
telling me L features.
remember just
I
how
like.
the matrix transformations go. But you got to remember that these are big matrices. They're not.
Right. Right.
So 120 is how many like rows it has, I think.
But yeah, 120. I don't know how the compression works. That's their math, right? Like I don't
The
know.
compression is it's magic, yeah.
Yeah.
Well, actually, it's not that magic, but it's kind of magic.
Yeah.
Actually, what?
As far as
So
the
yeah,
feed forward part, so relu is like an activation function. it's a rectified linear unit.
It cuts off at 0 or something, right?
Yeah, so it cuts
Or-
off at 0, and then it's like linear afterwards.
Right.
Basically, I think it's just to kill out like the overly like useless features, right? And just
Mhm.
I mean anything that sort of like passes the test kind of stays. That's kind of how I understand it. But you should also note that I still haven't taken linear algebra.
Right. No, I mean they don't teach any of this in linear algebra, at least for us. But
Yeah.
Yeah, I don't.
This
Yeah, I mean,
this
your
as far as I'm
explanation of
aware,
it is
this like the activation function, the purpose of it is kind of like as you're passing through the neurons in order to kind of like speed the process up. You kind of want to have like a threshold, like this is sigmoid, where let's just go sigmoid ReLU.
yeah, the second picture on the right is what they use because they say like you cutting it off is not a good option, and so they try to like extend it a little bit if like the leaky ReLU.
Mm-hmm. But
They kind of use that because sometimes if you cut it off, it's bad. I don't know.
But as far as I'm aware, this kind of just this like the activation function. The purpose of it is just to pick out to get rid of the bad features, like the overly bad features. I've heard that there's issues with sigmoid in the sense that it's the threshold's really high, and then those are like super overvalued.
Basically, you're just multiplying every derivative you use for backpropagation by that function, or not multiplying. You're just applying the function to it.
Yeah. Okay, that actually makes a lot more sense. But that's probably something to do with the descent. Oh yeah, see so. Oh, now it makes more sense. So as we feed forward, right, we're pulling over it by using the ReLU function for each convolutional layer, right? So we'll kind of go over each kernel. We'll use ReLU on it, and then we'll pick out what we want.
Mm-hmm.
And then the same thing will happen with this second convolutional layer. So that makes sense, right? So
Yeah.
we'll get the image. The image kind of goes through the convolution, and the actual thing that we're doing, the math has to be ReLU, right? And once we do ReLU, we're actually pulling over it, right, with the same max2 function that we pick out the highest value. So if I had to do like on actual paper, I'm sure I'd fail that test, but it kind of makes it a little bit more sense now that we're picking the highest value using this right, over each 4x4 section, right? And by doing that once, maybe twice, we can sort of get a better idea as to what we want. The view part,
That's just matrix transformation stuff. It's like
sure, but I think this is what actually flattens it, right? That's why it's -1.
that sounds right.
And then we'll ReLU it again with the linear layer. We go from that 120 channel, and then we kind of call FC2 on that 120 channel to get 84. Final thing we do is to actually get the predictions, right? And that would be to go from 84 to 10. And that would be
I think we should
our
take
network.
out the FC. Oh, we kept the FC2. Okay, that's fine.
See, what I'm thinking is that this model is probably way overkill for MNIST.
Oh, probably. But what
Because it's for CFAR10, right?
this is for CFAR10.
Yeah, so CFAR10 is like not black and white. I think it's higher resolution.
Correct.
It's I mean, from what I saw, the images are also 28 by 28.
Well, at least it's not black and white, and I bet that makes it all harder.
Yeah. Okay,
So
so
I'm thinking that we could probably do MNIST with like 4 layers.
you want to drop this? We can play around.
No,
Honestly, the whole
let's
point is
go
just to
with
learn,
this.
right?
Let's go with this. Because
Huh?
like we don't want it to be too underpowered, right?
Yeah, that's okay. I think the first thing was just to learn. But as far as this cross entropy loss is kind of how we're comparing stuff. So you'll notice that when I define classes, each one is going to be for the number that we're given. The way that it'll predict it is that it'll predict it'll predict 10 numbers, but in each pot it's like the confidence of how confident the thing is. And you'll notice that it's going to be really bad at first when we look at the loss. And the whole point is just kind of like instead of certain sort of things where if you've ever done like regression with like just like a bunch of data, like if you took an AP stats or whatever, you kind of only get like one line that works best. But I think cross entropy kind of works in the sense that it'll work better for categories where it's rewarded for predicting the right category rather than choosing the path of least conflict, where if you had to imagine like a neural network picking out a number that would usually or like most often be wrong, most often would give you the number with the least amount of loss, it's going to pick 5, right? Because that's right smack in the middle. and so chances are the loss will be the least for that.
Yeah, so as an example, right, I tried to make a freaking Pong AI with ML, and it just kept the paddle in the center.
Yeah, and I did a one for facial recognition, and it basically just, and the way it worked is like there's 4 categories. Or one was white. It was white, black, Asian, and Indian. Like those were the categories, but it was 0, 1, 2, 3. And so I just trained it just to predict the path of least resistance, and then it just told me everyone was black. So
What loss function did you use?
it was MSC. So MSC, mean squared error, is just
yeah,
to
mean
predict
squared
the path of least error, and that's actually the
Correct.
loss function that we're using in our code right now. So we might change that.
Okay.
This should be fine.
So the
What comes
optimizer,
next?
I think we should explain the optimizer, right?
Sure.
So the optimizer SGD is standard gradient descent. Basically, it's just taking
Stochastic?
what? Oh, stochastic. I
Oh.
thought it was standard. You might be right.
It's stochastic.
Anyways,
It's stochastic.
Okay.
all right. Yeah. So basically, you're just taking the derivative at each element, and you're just multiplying and adding it, multiplying it by the learning rate and adding it.
Correct.
And I forget exactly what the momentum is.
Yeah, I
but it
didn't know what the
basically makes it so it doesn't get stuck. But the thing is that SGD, you'll find yourself wanting to change the learning rate a lot. At the
Right.
start, you want your learning rate to be high, and you'll start lowering it. So actually, an optimizer which is objectively better than SGD is called Atom, and it just uses some heuristic to change the learning rate.
Okay.
But yes, factual.
Wait, actually, might as well just change it, right?
Sure. Let's just look up how that works.
Yeah.
Atom optimizer PyTorch.
Yeah, so you just use model.parameters, and then I think that's all. You don't even need the learning rate. It's optional.
Okay, but I guess the next thing is var1, var2. That means that we have to put in the actual class.
No, var1, var2 are placeholders there. So you can just use net.parameters. And then you don't have to set the learning rate because it's optional.
That's the right way to put it in.
Yeah.
Okay, let's... No error, and that means I can code. Do you want to, do you want to activate CUDA for this one? I can import. I think it's PyCUDA.
How much of a bin you think it will be?
I don't even know if I did this right. Oh, fuck it. If I don't know how to do it, I'm not going to do it right now. I'm not going to waste. I think though, just to do it, torch.device.
Yeah.
Device name. It'll tell you, I think, right? I guess this will only apply if you have an NVIDIA GPU. This really only makes a difference then. But you'll kind of be able to tell if you can use it. Yeah, so for me, I have a 1660, right? This was the computer I built. So that's something I can use. CUDA, I think you have to get is available. Yeah, that's definitely. So I can use CUDA, and that can make things speedy, especially if we're dealing with stuff like imaging. This won't matter too much right now. I think most of us will just train it on our computers and then see how much we profit. But
Okay.
it's just important just to know that like the stuff that they talk about CUDA, there's ways to activate it, and should you have CUDA, like an NVIDIA GPU on your machine, I think you will be able to use it. Yeah, we can. We don't have to use CUDA for now. Yeah. So. With that being said, do you want to just go? I think we can just go to straight training the network.
Yeah.
Let's go through line by line before we actually do the magic. It's pretty well fucking commented. I don't have to do that much work. But, okay. Epochs are just how many times we're going to go over the entire data set just to train, right? This time we're only going to go over it twice. Sometimes, at least with the one I was talking about, the facial training, I did it like 10 times just to get shitty results, but whatever.
Okay.
The same way that you saw, we did data iterable, right? The data loader that gave us 4, because that's kind of how we specified the batch size.
Mm-hmm.
If we enumerate it, we're getting the index and the actual image, like the image values
Right.
of every object in train loader, not just like a single group of 4.
Okay.
Each time we call data, that's a batch size of 4. So you can consider this as being a iter of train loader every time we call it, right?
Mm-hmm.
Right, and that would be the inputs and the labels.
Right.
Optimizer.
You're
This is
clearing out the
important just
gradient.
because this is changing the gradients, right? So this is changing the weights every time.
Yeah.
Every time
Yeah.
we'll go through, and that kind of helps because I think if you have bad predictions or something like that in the beginning, it'll help the neural network actually learn faster, I believe.
I think I read this somewhere, and it's basically like you don't want so these gradients at each iteration, you don't want them because they basically accumulate on the previous thing, and so you don't want that like you don't want each time that you fix the neural network that it's accumulating on top of the gradient that was there in the previous iteration. I don't know if that makes sense. I just saw it in a video. I don't know if that makes sense.
Yeah, that's basically it, right?
Let's change what this says then. So optimizer
Yeah, I
0
mean-
grad.
So if you're like moving, you're changing the matrix. You don't want to keep the derivatives the same.
I think maybe I can get a better explanation next time I look at it.
Don't worry about it. So that's fine though. It's just kind of it's just to know that it helps the network predict. Now we've got the outputs on our network. This is passing through the network. So all the stuff that we talked about before, where we get the imagery, right? We're gonna pass it through, and that's gonna give us a prediction. It'll kind of come out as confidence in each, like the confidence in each number that it's gonna predict. We'll send that like training data. So we'll compute the actual training data between what we actually predicted. Where say it wasn't very confident. I'm just gonna say 0.01. That actually sounds very confident. Like XYZ, right? But it's just gonna compare this output data compared to the actual labels, and the labels are actually really confident, right? Because it's literally just 0, 0, 0, and then the one that is actually correct is 1, and everything else is 0. I believe that's how it should look. When we go backwards, that's backpropagation, and that's the actual process of learning from the error. I can't really.
Right.
I'd be lying if I said I really know the math behind that one. But I guess the last part is kind of like the more intuitive part. Like we said before, we're gonna go over the data loader multiple times, and what we're trying to do is actually check. We're gonna check periodically how it's doing. This is just the running loss is just every time we mess up, we're gonna calculate how bad it did, and then we're just gonna add it. When we do every 2,000 or so runs, we're gonna print out this is how poorly it did, right, divided by 2,000. Because if you can imagine, the running loss is like the average loss, right, over the 2,000 batches.
Right.
And otherwise,
What is the size of our data set?
I did not check that. I guess I could check though.
Maybe it's not a big deal. I don't know.
No, we could.
I was just talking in terms of the 2,000 examples.
Let's just see how bad it is.
It's 2,000 times the number of times it prints out the running loss.
60,000.
Okay. Yeah, 60,000.
No, I hope test set is smaller.
So maybe we
Oh,
should
those are
make our.
fucking huge. Maybe I should use CUDA.
Yeah.
I'll cancel. Worst comes to worst. I'll kill the cell or something. But yeah, this will be a nice learning journey. Let's kill it. Let's just see if it runs. Usually this is where I get the most errors. Oh,
Yeah, it'll take
but yeah. This is the boring part. This is the actual thing of it training. That's good loss right there.
Wait, so how is loss represented? Like, how is this? So 0.982. What can you deduce from that again?
How bad the network is? Higher loss is worse.
Yeah. So if it's close to 1, that means it's bad. That means it's bad.
Yeah, I don't know the actual calculation for what is it, cross entropy, but you can imagine. So MSE is in the name.
Oh,
It's
okay.
mean squared error. So say that the
Right,
value
right.
you're supposed to predict is like 5, and you predicted 1. The error in
Yeah.
MSE would be
Half times this minus
0.5.
this squared. I remember.
right.
Mm-hmm.
I guess I can just.
I think it's the whole thing subtracted, so it would be
Yeah,
like
wouldn't it be
25
the
minus
first
1,
minus the
whole
second
thing
one squared?
Yeah.
Because the loss, if you have some of them it predicts up, some of them it predicts down, you don't want those to cancel out and give you a loss of 0.
I was under the impression this is how it works.
If you look at the equation of mean squared error, it's just basically, like it's a very simple, the hypothesis minus the actual thing whole squared, and then you have a bunch of.
And
Where is
basically,
it?
you're just taking the absolute difference, but instead of using absolute value, because absolute value doesn't have a derivative 0,
Correct.
Oh yeah, I apologize. But I guess the
Yeah,
spirit
you can
of
see
this
this loss is reducing. Cool.
Oh, this is fine actually. This makes sense.
Yeah.
So then I guess you'd want to keep training until your loss was at least smaller than the difference between your categories, or significantly smaller, to where that, like, the difference is such that the probability of it guessing wrong is at an acceptable value.
Let's see. Let's just. So this is the trained network, right? I'm show. Let's
I think we can
print
just predict the
labels.
accuracy of the network.
Yeah, this is the part where I'm gonna try and find out how accurate it is.
Okay. So,
That's kind of what we saw before, right? We're just gonna predict the actual imagery. Oh, sorry. Let me go over it. I mean, you've seen this before, though, right? We're gonna do the same thing where we pick
Yeah.
out 4. We're gonna print them out, right? And then we're just gonna come see what the actual labels are. Let's look at what we got to offer. So let me just. I guess I can explain this part too. So right here, as we remember before, when we're picking out the largest values in each torch prediction, we're gonna print out from that pot of like 9 predictions, like I said before, where 0, 0, 0 point. Right. We're kind of just gonna pick out whichever one's the highest confidence, because that's the one that we think the network's predicting. And then we're just gonna see how it did. Sick.
right.
All right, and then let's just copy their final thing just to see.
The accuracy. Yeah.
All right, let's go through this. Important that there's no gradient. The same way before, we kind of don't want it to build up over time. I believe that's the right way to do it. Kyle, you can correct me if I'm wrong. But basically, we're just going to go over the entire thing. Print out whatever imagery label, have our prediction, get the prediction, and then compare it. Actually compare it do the thing. The one thing I do want to see before print predicted. I just want to see if they're the same data type. So I don't know if they equate to being the same. Let's just compare and see. That's fucking solid. Let's do it one more time. Does it only do the... I thought it's randomized.
Yeah, I thought too it was random.
Whatever.
Oh well.
That's kind of the point I wanted to get across, though. That
Mhm.
it can be kind of a linear process. I guess now we are kind of done with this. Do you want to do anything else? Do you want to start changing and trying to optimize it? Because we kind of just did a basic thing just to get it working. We can play around with it right now if you guys are interested.
I guess you can just test it on the test set. I don't know, because it looks pretty optimized. I don't know. I mean,
MNIST is
maybe
supposed
not
to be
97
easy.
is not the greatest.
No, yeah, MNIST is supposed to be easy. I think if you guys tried the tutorial, the fashion,
Yeah,
or not
it's
the fashion,
hard.
but the actual the car plot, whatever, they get like 50%
Right.
accuracy, right? And but it's kind of like
Sure,
harder
yeah.
images. It's not only is it gray, not only is it not black and white, with a bunch of imagery, the categories are super different.
Yeah.
Car, ship, plane. With that being said, do you want to try something harder? I can kind of show you what I tried to do recently that has been just fucking ruining my day.
Sure.
All right, let me kill this one.
So a ref.
Yeah.
This net, right?
Mm-hmm.
Oh gosh. Let me see if I can try and understand this.
Oh yeah. Actually,
Anyway,
that's
but-
actually a good thing. Does everyone? Okay, I guess there's only 5 of us, right? Dom, how do you feel? Alec, how do you feel? I know Big Dash is a little bit more confident, but he also has like years on us as far as math
Yeah.
knowledge.
Oh no, I don't have any knowledge. I think it's just all this knowledge. I guess is just from that Coursera, Stanford thing.
Andrew Ring. Alpha fucking male. But yeah, as far as Dom Alec, do you kind of want to run this through again, or do you want to try like I guess something where we're all struggling?
Well, I don't have much experience like at all with machine learning.
That's
So
fine.
like none of this really makes sense.
Okay, we can kind of go over. Okay,
Yeah.
there's just a couple of basic things that we should kind of understand and categorize as, right? First step is loading data, right? Like like I said in the game plan, this first sort of month is just going to be finding out how to properly load data into our model, right? And that's kind of it's perfectly done for us. They literally have it pre-built in so that everything we need
Yeah.
is done for us already, right? In the real world, I think it's going to be significantly harder, and that's why it takes like years to generate these MNIST data sets. I think this MNIST data set is like over a decade old. I searched that up. There's like a Wikipedia article. Yeah. $60,000. I'm trying to find the actual 2004, dude.
Jeez.
So it takes a while, right? And that's okay. But that's like a big thing to notice that like one of the most important parts of machine learning is good data, because it's like you can have something trained for hours on end, but if the data is garbage, it's not going to give you anything good, right? And that's kind of setting us up for success. Once we actually get a nice data set, we can put it into these forms of train loader and data loader. Train loader and test loader, right? And that's just kind of iterating. When we want to train and we want to pull a call from more data, this is kind of the object that we're going to use. Just kind of incorporate all of this in your mind as just being, okay, this is data. This has nothing to do with actual machine learning. This is just nicely formatting things for later. Classes, I'm sure you're pretty confident on. They'll change based on the objective you want to achieve, right? With this, we're doing something where we are trying to classify something we're seeing. That would have to deal with numbers, right? They're classifying them from 0 to 10. As you can kind of see, 0 to 10. This is just purely for demonstration purposes, right? We can wax on, wax off, send this out into the garbage truck, right? This doesn't matter. This is a little bit more important. to be honest with you, I would be lying if I said I knew how this part works. Really what I want you to know is that the image processing, in the sense that this is how we pass over like an image, because you know what an image is, right? It's just a bunch of pixels.
Yeah.
That as far as processing images into smaller things for a machine to learn from, that's what happens here, right? And here, how the machine actually learns and the functions it's calling happens here.
Okay.
So there's two things, right? How we pick up data for a machine to learn from and how the machine learns from that data. Those are sort of the two things that you need to classify. So we started with data, right? This is how we get data. This is the actual object that's the machine's going to learn from, right? This is a little bit kind of more the same. If you really want specific things, this is the number the machine's going to learn to, this is how like the number the machine will judge how well it's doing based off of. And this is how the machine will learn better. I don't know if that was right. But I kind of incorporate all of this as like the architecture of machine learning, right? More so than getting data and training data, like training an actual machine. This is building the machine from the software ground up, right? And that's what really happens here. This last part is training, right? We're going to do the running loss. We're going to train. Look, again, I'd be lying if I said I knew what this math do, right? But kind of get an overarching idea that this, all that's happening here is the machine actually doing the process of learning. To kind of draw a tangent to that, let's pull up something that I think will help. AMPS. When we split up into February, March, and April, right, it's kind of the same thing where February is going to be boring because we're just learning how to format data for a machine to learn from, right? We kind of did the first process where, okay, from an overarching thing, the PID controller can drive a car, right? We're going to have to do more kind of lame work where we're kind of getting data that's ready for a machine to learn from. And that's because it's hard, right? 2004, bro. Like, we were 2 years old. Next thing will kind of be with the architecture, right? We're going to have to make that first model. It's probably going to suck, right? Chances are there's not going to be 17-year-old data to use, right? So the first model is probably going to like suck, but that's just kind of learning architecture and then doing better with that. When it comes to April, that's when we're training and actually getting something successful, right? We can successfully predict paths and get the results we want. And kind of in the same way, we're going to get data, we're going to learn how to build something, and then we're going to actually test how strong our building is. Hopefully that helps a little bit more. You'll definitely have to learn by doing, because chances are, just like you, just like me, you probably haven't taken multivar lineage, right? I'm just taking multivar right now. So I'd be lying if I said I really knew the math behind any of this. But I do it until I see something connect, and then I pretend I know.
Alright, yeah, I'll look into this thing that Alec put in.
Yeah, I think
watch
I
those
haven't.
videos.
I personally haven't seen all of those videos, so that's probably part of the reason that I don't really know what I'm doing. But every person I've talked to, not every person, but a lot of people that I've talked to have recommended his videos, and I have watched the first one on that. That's sort of like an overview on machine learning, and it will bring you from feeling like you're feeling around in the dark into like, oh, okay, I see what's going on. I just need to fill in the details.
Yeah,
So
he also talks about gradient descent in the second
terms of-
video. Yeah, he does a lot of the math too. Sorry to cut you off. I watched that and that
No,
also
no,
opened my eyes.
Yeah. So and then could you go back to the structure of the net? Back up there, yeah. So I guess my understanding of this would be the convolutional network takes the just like colors of the image or brightness if you're using grayscale, right? And then I think because we did a little bit of image processing in my my 133 class, right? And then so it does like applies different filters on it to detect different things. So like we did edge detect. Which one did you guys all do edge detection?
I did that in 133.
Yeah, so like edge detection is one of them to detect edges. So then like one of those like dimensions hypothetically would be like edges maybe, and then
Yeah, yeah, that's right.
another
That's true.
yeah, and then another dimension would be like curves or
Corners.
a
Yeah.
circular shape. And it would like they would detect different features, and then the linear layers would take those features and combine them together and say, okay, well, if I have 4 curves plus 3 edges, then that's going to give me whatever shape, and sort of take those rough feature like image features and put them together into actual concepts.
I think
Did
that's
I
good
get
thing you
that?
mentioned that. I bet.
Okay, like,
I wouldn't say
sort
this
of right.
I wouldn't say this with complete confidence, but I bet that's kind of like that's why we go from 120 to 84 to 10. Because if you went straight from 16 to 10, it's kind of just saying that there's only one thing that can come out to each value, from the array value 0 to 10. But if you start with 120, you have a whole bunch of features to work with, and then you want to say, okay, let's say that those 120 things that allow us to guess certain things, let's just guess 84 things with these 120 things, and then we're going from 84 things that we can guess about based on features to 10. But I think
Right,
that
so I
slow
think
sort of process allows you to pick out stuff, and I believe that's why you kind of do the same thing with Relu, where you're starting with 120, right, and then we're picking out features that are just the very best for the 84, and then we're picking out from the 84 the very best for 10, and then that's kind of how we give out the 10 to predict.
Yeah, so like based on my knowledge, which I totally like, it could be flawed, right? But like my sort of thought process through this is that those 120 are, like I said, like either edges or curves or maybe a single yellow pixel in the center of the screen, but they're just random features. And those 120 are then combined together to say like if you have a curve and then a straight line, that makes a different feature, and each of those features are part of those 84, and then those 84 go into 10, and those 10 are I think those are 10 digits. The
Yeah,
digits
they are.
0 through 9.
So you're basically right. At each step, what's happening is a matrix multiplication, and these matrices have lots of numbers in them. And basically, you're just trying to find out what numbers give you the answer you want. So you're going from your 120 aspects, right? Like the edges, the curves, whatever. And it's pretty much impossible for us to find out what it's actually detecting. But basically, you're taking all of those features, right? And then you're saying, okay, so let me take it down to 84 of those features, right? And then you're taking it down from 84 to 10. And then those 10 features, you're constraining them, right? In the training process, when you do your back propagation, you're constraining those 10 features. You're saying, okay, this first one has to be 0, the second one has to be when it looks like a 1, etc. Right? So basically, Alec got it right.
Okay, and then
Wonderful.
for the forward, that would be when it's comparing itself with the training data, and the forward
so-
would be adjusting the weights of each of those connections. So
I mean, init doesn't actually do anything.
Those are just the things you actually call
it's
in
just-
forward.
Yeah.
Right. So you'll
it's just-
notice that it'll say conv1, and that's just calling the conv1
Yeah.
thing, the con2d layer, right? To kind of pull through the image. And you'll kind of notice that we would assign that back to x. So if x was just like the line of numbers, right? This is just pure numbers that we're sending to a machine. The machine kind of just does the processing thing. I think the real magic will sort of happen after here, but just to finish my point, like we said with init, right? Conv1, that's the first processing that we're gonna do. We're gonna pull that same thing that we said before, right? These aren't actual things that are happening. These are just definitions the computer can use later, and that's just to pull over the thing that we convoluted over. So we're picking out certain values in like the 4x4 section in each part of the image. We're going to pull that over, right? And then that's going to be what the actual line of numbers is now. The second time we go over this line of numbers, we're going to do the same sort of kind of convolution, right? We got 6 channels this time, but that doesn't really matter, right? We're going to convolute it over, pick out the values with math. Well, and then by picking out the most valuable-ish features, we set that to be our new line of numbers. before we were doing a 28 by 28. Right now, you'll kind of see that's kind of how we flatten it to a straight line of numbers. And now it kind of comes to what Alec was talking about, I believe, where we kind of go from here are 120 features based on any image we take in, right? Here are the 120 things that we consider valuable. And we did that, right, with self FC1, where we're making this thing a straight linear line. I think that's why it's called linear. And then we're going to kind of go with that same sort of activation function that picks out, that says, here are the, lines, edges, right? And then the same thing that kind of happens with the 120 features coming down to 84 is happening where here are the corners, here are the curves, right? And then with self FC3, you'll notice that we don't actually pick out certain features, and that's just because I think we're just condensating those 84 into what it actually means as far as the 10 predicted values, right? If there were 10 pots that are predicted, and that's his confidence in it being each number, so there's the 0 pot. Sorry, I lost where I was.
You're fine.
That's not what I wanted, computer. Right? It's going to predict his confidence in each pot, right? And that's just sort of combining, hey, these features mean these certain things. I'm actually going to say that from these 84 features, this gives me a certain level of confidence in it being 0, it being 1, 2, 3, 4, all the way up to 9. I believe that's correct. Now, to someone that actually knows linear algebra, can they correct me?
So, well, I don't know that I could say I know linear algebra. I took linear algebra. I don't know that I know linear algebra. But from my understanding, the only thing that I know that she said wrong, I think, is that the linear layers are, the reason it's called linear is because like linear combination. So each of those 84 features would be a linear combination of a linear combination of all of those 120 features. It's just some of them may be 0.
Correct. Yeah.
And then, so yeah, you'd just be doing linear combinations. And then the forward is going to adjust those coefficients in front of each of those 120. So if you have a 1, then the curve feature, let's say there was 1, the curve feature in the end node for 1, that's probably going to have a value that's very close to 0. So if it sees curves, it's going to say, okay, well, that doesn't translate into a 1, right? Can anybody confirm or not confirm?
Yeah, I get it. Yeah, I get it.
Well, not even understanding just whether or not I'm right, but because like I said, I'm not the expert here.
The thing is, I mean, everyone, even I've taken linear algebra, but there's a specific type of math about what these things do, and I haven't looked about what they like. The math behind this, the ReLU or the convolution. Like, unless we know the math behind it, I don't think you'd be able to explain exactly what it's doing.
So in terms of convolutional, I'm just gonna paste like a link to the convolutional neural network implementation in my grad.
This is the summer program?
Yeah, I mean, it's like pretty long, but it's also fairly well commented and understandable. You have to understand how like NumPy stuff works.
That's fine though.
Oh, I didn't catch that code color there. I thought the comments were going to be green, and when you said it was well commented, I don't see any comments in that entire code.
Yeah.
I got a little concerned until I realized, hold on.
Yeah. I mean, it is like kind of. It'll definitely like take some brain power to figure out what it's doing, but it makes sense. I mean,
sure.
Like you gotta look at it with the Wikipedia article side by side. Like.
But that's kind of like the overarching view. I think the big things are just really take away, or kind of, I don't know. Like I feel wrong saying this with like any confidence just because I don't actually know. But kind of to me, the big things that I usually take away are like, okay, first step for me is always just getting data ready for the actual thing to process, right? And that's kind of it's easier done here. It'll be harder, I guess, later. But it's just formatting data for the machine to learn from, right? The second part is actually building the architecture, and that would just be, okay, this is how we pass through images and get what we want and whatnot, right? This is the math to learn it. Again, don't really know. So just know it like, okay, this is how we're gonna actually get images to learning. And this is how we're gonna do learn to learning. Architecture.
All right.
Last part is just training and evaluation, where we can all train, right? We can all just run this code through. It's just this probably is more frustrating for me because at least with the one that I was doing, I just keep running into syntax errors and I don't know how to fix it. But that's kind of the last part. With that being said, if we all are down to stay longer, we can try one that I kind of hated, but
I actually gotta go in like 10 minutes.
Yeah, I gotta leave. I have something to do at 8:30 for my senior design.
no, that's fine. We don't have to stay. I just, if this is kind of the end, I just wanted to ask, how does everyone feel about writing, or how does everyone feel about looking through code on a CNN? I guess that's the first step, right? And then the next step would just be writing it. Because looking at it, like, let's just say we looked at the classifier right now. Let's put that in somewhere. Like, just without even reading it, it does feel similar, right? In the sense that, okay, so we saw that before. We know what this means, right? We know what, like, this is kind of doing. We're just preparing data for it to actually run through. Next thing, this is not necessary, but this is just getting a peek under the hood. Now we know what it's like, right? Bird, deer, truck, plane. And we know how this is done, right? We're going to go through some images. It's going to be a straight line of text, right? But what we're going to do is first, yeah, we'll make it normal or whatever, but we're just going to plot these on a grid, and then we're just going to print out the resulting values. The architecture, we have a better idea as to what it actually means to convolute over something, pool over something, convolute. Linear combinations, not just fucking lines. Right. Pool over something with the actual convolutions we're getting and doing an activation function to actually sort of deduce meaning out of a number. Next would just be fancier things. Next would be fancier things to actually help us learn in the process. Each time we're doing this, it's just something that we're just doing to kind of cut down from image to prediction. And now this is how the predictions get better, right? Training it, it's basically the same thing we had. I don't think we actually changed a single thing. But this is the process of the machine learning, right? We're going to get our data, fancy things, but basically just resetting our progress. Prediction, evaluate how we did, fix the problem, and then move forward, right? And then we'll evaluate how we did. Testing it, I mean, we did that same thing where we can pull out something, and the same way before that we saw a grid of things, we can actually see the grid and also see what not only what they're actually supposed to be, but what the computer predicts. With that being said, that was very fast. How did you all feel?
I think it's okay. I don't. Well, again, I'm speaking for myself.
I guess the one thing we should do then is that I think everyone should try to code the one thing on their own. If we want to do something like this again, I would be more than happy to give you the problem I have been too lazy to solve myself, and then we can see as a group what it's like to actually get something going from the ground up with with less kind of hand-holding from someone else's code.
Right. Yeah, for sure.
And then we can, I don't know, hold hands, sing Kumbaya. I guess that's really it. Because I think if you look through the model code now, you'll have a better feeling. Matter of fact, before we leave, let's actually do that. It's model.py, right? Let's just look at the net, right? Basically, the whole thing that seems so elusive for an entire semester, that actually doesn't matter. This is it. 30 lines of code. And that's the whole thing that we were kind of like freaking out over the entire semester. We're convoluting, right? The same thing we saw before, RGB image, right? We're going to pass over it. Print out 24 channels. I guess that's a lot of memory for the computer to learn from, right? Stride 5. Or sorry, kernel size 5, kind of the same way that we had a kernel size 4 for our imagery, and then we strided over it. We do that a whole fucking lot of times, but really it's kind of more of the same, right? The pooling was the exact same as actually our code. Dropout, if you remember, Mikhail said that with big numbers like this, it's very likely that it'll just store very specific predictions into specific areas, and then it'll just know how to print like one type of specific thing. The reason why we changed dropout is because the neurons that only know very specific things will actually overfire for regular scenarios and kind of give bad predictions because it's kind of overtrained for one specific scenario and kind of predicts that same thing all the way throughout. Dropping it out kind of cuts out the value of what those over-specified neurons predictions would be and kind of gives us a better holistic view. Linear combinations, we know this actually, as a matter of fact, right? We know this. And that'll give us a prediction. The same way that we're looking at forward, we see the same thing, right? We're doing some sort of thing where we process through what we've seen before, and we're applying a convolutional thing that we know, we're picking out the greatest values, and we're doing that over and over again. We'll just we'll kill some of the neurons, right? Because it's overtrained. Probably bad architecture, but same thing we saw before, where we go from like very specific things that we kind of pick out from the image to flattening the image, and not only that, picking out linear combinations to get the final value. That's the code we have right now. But I think we all kind of have a feeling as to what we're looking at right now, right? Hello?
Yeah, I guess.
Sorry.
I probably should have. I don't know. At least tried to understand some of this before.
No, but that's okay. That's okay. This isn't like a completely different language. You can understand that you can learn this though, right? It's not like difficult in the sense that it's not like it's beyond us at the moment. Give it a week.
I just
give it
meant
2 weeks.
like
Shit, give it 3 weeks, right? But it's
learning.
doable.
Well, I mean,
Yeah.
if you never coded in Python, it kind of is a completely different language.
Well, I have.
Hello.
Ha ha ha!
I'm sorry.
No, but I think that we're in a lot better of a prediction place than we thought. I think just wondering, Mikhail, you changed this, right, just to actually have 2 predictions?
Yeah, I did change that actually.
Yeah, I just want to
I think I had to change something else because I changed that though.
This is just fancier stuff, just pulling from different files. That's some stuff we can recognize though, right? Optimizer.
I mean, CFG is just like fake, or it's not fake. It's not a PyTorch thing. It's just some random class, I believe. Right?
What do you say? It's struct. I don't know what struct is though.
Oh, struct is just a freaking.
You just make a
it's-
structure. I don't know.
Yeah, it's just like
Yeah,
a Python
alright.
destruct.
it's-
It's fake. It's literally
Structs are
just
just
an
like
empty.
normal coding things.
Yeah, normal
Yeah,
structure.
yeah. I
Yeah,
mean, it's just because
It's a normal code thing.
Yeah, because Python doesn't have structs; it has classes. So someone decided to
Mhm.
make a friggin'
Class. Hey, that's one way to do it. So yeah, struct's just like a class without methods.
But I don't know. I feel like the rest of this is all just like random stuff in Python that we'd have to learn, right?
man.
I'd be
sometimes
lying if I said I really freaking know.
so- It's pretty simple to understand. It's just
Yeah,
Python
but
stuff.
like, you know what I'm saying? Like, oh, just knowing what the plot PNG is actually calling or whatever. Loading data, we can all learn how to do that, right? Some of the stuff we normalize. We've seen that before, right? But train
Yeah.
loader, test loader, this is fine, right? This is all fine. We did define train.
And you're going through that 4 epoch loop is basically what, or not the same,
Yeah.
but same
We can
structure.
pull that up afterwards, actually.
Actually, all neural networks look the same.
They do,
Right,
right?
right.
So I think this good first
Actually,
exposure.
that's a lie because recurrent neural networks don't.
Mm.
Are we trying to do it? I don't know if we can do it. I don't know how to do recurrent.
I'm pretty sure actually
Kind
the way PyTorch works, we might be able to do LSTMs.
All right, but this is kind of. I feel like this is kind of like we've seen this before. Like we've seen these words before, and that means it's doable. Right? Yeah.
Sure.
Load data, train, and that's all that we're doing here. Where we're just calling. Maybe I shouldn't be so confident, but.
So
I think it's doable. I'm optimistic about that, right? Because look, in a day, like you can at least get the first glimpse of code and understand that here are what certain words kind of lead me towards, and the rest I can sort of Google and start to connect dots. So I think in that sense, I think you are in a much better position than you believe you're in.
For sure, yeah.
yeah. Hey, not to curb your optimism, but like, does that structure have any hope of like predicting what we want it to predict? Because
As far
the
as
way,
waypoints,
yeah, like the waypoints have to be related to each other, right? And like, you have to plot like what, like 5 of them per frame per like output.
no, we can't.
Yeah, I think we have to change
Think about
this
it. Okay,
Depending
so
on how fast
imagine
you
if
run it, I guess.
instead of, imagine instead of like classes being what was it? Classes just being like a set list of things. We can imagine that each waypoint would just be a different.
I mean, I think the issue is that this is a classifier. We're not making a classifier. We're making
Correct.
something else.
Oh yeah, actually.
Right, like you can ask it for 4 values, but like that doesn't mean they're gonna be good.
But the
Yeah,
thing is
yeah,
that
I
the
think
neural
we're-
network we have, right? The current model is not a classifier either.
It's not. It's we use MSC actually, right?
So right now it has 2 outputs. It could output, let's say, 20 values. So it could be XY, XY, XY.
So the 2 values was speed and throttle? Is that what
Yeah.
you were doing? Okay.
Yeah.
So yeah, well, wouldn't we would want it to output
Like 10 XY
waypoints, but then
coordinates.
the X and the Y would have to be related. Wouldn't you have to define somewhere in the structure that those are related? The X and the Y are
No.
related,
No,
or would it?
it's
that
just
itself?
neural network magic. It will figure it out.
That's wild. All right.
Yeah.
But I don't know. I feel like the fact that you can ask these questions instead of how does it predict period, I think is a kind of a step in the right direction.
Yeah.
I should have a cap.
Yeah. Well, unless you consider that I don't know the answer to the first question either.
What was
But
the first
You
question?
can though, like give it like
How does
one
it
weekend of just
predict
writing a neural network for yourself, and you will literally be able to do that. Look, like let's just
Yeah.
review, right? Team worked together to build.
nice.
Right. But really, it's first everyone's sort of first exposure to seeing a classifier built from the ground up. Exposure to essential. Alright, because that's the thing. Like we had exposure to pretty essential concepts, right? Loading data, building CNN architecture, training, and evaluating performance. This week, everyone has also looked through PyTorch right? And I think looking at it from that perspective, I think it's better than you think. From this sort of perspective where you can, quote unquote, build a CNN, right? You had exposure to seeing something being built from the ground up rather than just hundreds of lines of ew, right? So rather than hundreds of lines, it's maybe 30, 40, maybe 100, but it's double digits, right? Double digits max size of code, right? So you can kind of see something connect rather than just looking at something that you don't understand.
By the way, RF, I think you should post that notebook.
It is. So it's under the Google folder. I will post this as well. I'll post this. You will actually, I think, all be able to see it. At least people who are on the team last semester. I'll push it to this learning projects, and the thing I'll name it under is the MNIST thing. I haven't pushed it yet, but I'll just say
Yeah.
we'll call it MNIST. I was gonna say fingers. Numbers. What does that mean? XRSF?
Oh, that's kind of whack. That's like the cross-reference something, I think. It's like you're trying to use HTTPS to your localhost or something. I don't know if that's right, but it's just
yeah,
Jupyter.
I actually am getting that from my terminal.
But if it's already saved,
kill
right?
this for now, and
You can just manually do it through terminal.
Yeah. So this is fine though. So you'll be able to see it soon, hopefully. Let me see if I have public access.
Oh, do you have like HTTPS everywhere or something?
Maybe it's just whatever the hell Mozilla does.
I don't know.
So what I can do right now is it's public, right? So I'll drop the link to this, and everyone should be able to see it later today. Meeting info. Okay, so check that later, maybe like a couple of hours. I'll push it or whatever, but you should be able to pull this and play with it. But you'll have to probably pip install Jupyter or whatever, but as far as we kind of like reflect on today, you guys can see how a network can be built from the ground up. Being able to build this, whatever the fuck it was, is a different issue, right? But really, it's just saying that, hey, I can see what that might mean, and that might mean, and that might mean, and that might mean, right? So I think from that step, that's a big leap, right? As far as where you go from this, I think that's kind of up to you, right? Feel free to take the weekend to not only try that tutorial that we linked on Monday on your own, but just try to have fun with it, right? So I think as far as that goes, I think that's a big thing. Essential concepts, I think this sort of idea of loading data, building architecture, and training will kind of as an overarching view, apply to our project. I think we'll kind of see it this month when we actually have to try and formulate data from Unity to come into a nice CSV form, right? So things like that will come, but I think that we actually have a sort of better idea as to what we're going to do. You guys have all seen documentation either through me struggling or, I don't know, maybe on your own. So I think it's not bad. I don't know. Is there anything else anyone wants to say? We can kind of leave it at this.